The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So we'll start off by going over the Quiz 2 practice questions. So, 1.1, in Python, a subclass can override methods of its superclass. What say you all? True? All right. There are some repeat people from last night, so they know these already. Standard deviation, coefficient of variation are different names for the same thing. True or false? False. All right, 1.3. All right, so coefficient of variation. It is, I have to write big for the camera, so. Is that right? People who haven't asked the question. No, it's the other way around, right? Coefficient of variation is the standard deviation divided by the mean. What does this tell you? Like, what sort of information does the coefficient of variation tell you? Anyone? So it's another way of telling if your distribution is very widely spread. So what it's getting at is, like, it's trying to help you compare your standard deviation against your mean, because let's say that I have a distribution and its mean is all the way out at let's pick a very large number, right? So it's got a really big mean, but say its standard deviation is, I don't know, 100. Would you say that that's widely spread out? It's pretty tight, right? If you're taking, if this were like, an observatory taking measurements of deep space, and you got a fluctuation of 100 for your standard deviation, you'd probably say that was pretty good. And you wouldn't be too concerned about it because you've got a planet out there that's, billions of light years away or something. So, on the other hand, let's say that I have another measurement and its mean is somewhere around, say 50. And its standard deviation is 100. So it's a lot fatter. You would say that this has a much wider spread, right? So it's a way of relating the standard deviation and the mean. And rule of thumb is, if this is less than or equal to 1, we're going to say that it's not too widespread. There's not a lot of variation. Though that's the standard that Professor Gutak has. Depending on your purposes, maybe that's too large or whatever. So, but that's what coefficient of variation is. Everyone clear on it?
What's the difference between variance and standard deviation?
The difference between variance and standard deviation? Standard deviation is the square root of variance. All right. Unit testing is useful for debugging. What does the audience say?
True.
True? Okay. You know what unit testing is? Can you define it?
Well, unit testing is when you use other code to test your code, like,
Right.
yeah.
So you say you've broken your code up into nice little functions like a good programmer, and you want to make sure that those functions are giving you the right values. What you're doing with unit testing is you're writing a bunch of other code, or a little bit of code, sometimes a lot. It depends on how thorough you want to be in your testing. And what you have is known input and known output. And you're going to feed your input to the functions you're testing, and you're going to make sure that they give you the output that you're expecting. And if they don't give you the output that you're expecting, that indicates that there's probably a bug, which also kind of supports the idea that unit testing is good for debugging. And if you're very conscientious about your code and doing unit testing, you're going to run your unit tests every time you either run your code or make a change, because you might have inadvertently introduced a bug into the code that you're modifying. So it's a way of verifying, or it's a way of detecting bugs and also verifying that any changes you make in the process of, writing more functions for your program or modifying functionality in your program don't introduce other bugs. Okay? All right. So in Python, functions cannot be used as actual parameters. False. Why? Well, you could just rephrase the question. But a better answer is that functions are first-class citizens. So they're objects in and of themselves, and so you can pass them around to a function, and functions can make use of them. So we might see an example of that later on, if you want. All right, 1.5, increasing the size of a hash table typically increases the amount of time needed to locate a variable or value in the table. False. Why? Right, the hashing function is generally constant. Right. So, okay. Let's see. So, what does this code print? 6? It's 11. So what is the string X actually? It's the binary representation of an integer. And all this code is doing is it's just converting it to a decimal. Right? And because I came prepared tonight, sort of, kind of, I have the code here. And we can verify it. Any burning questions on that problem? All right, moving on. What is the expected value of G1? Anyone? Well, look at what the code's doing. Did someone?
Gauze. I haven't seen that function.
What's that?
What's gauze? That function, I haven't used that one.
Gauss
Gauss.
is
Oh,
a method
Gauss.
on a random object that draws a random value from a Gaussian distribution that has a mean at, well, in this case, mean, and a standard deviation of std dev, whatever you put in there. So maybe for this example, if I wanted to draw a random value from this distribution, which I said had a mean of 50 and a standard deviation of 100, I would, say random.gauss 50, 100. So in answering the question 3.1, what do people think? 100,000. What about 3.2? 100,000. So they're both the same, but they both have a different standard deviation. So what this is getting at is it's getting you to look at this. So this code is straight from the question, and all I'm going to do is I'm going to plot a histogram of what this function produces, and also I'm going to run it a number of times and verify that I am getting 100,000 in general. Python. There we go. So it's not exactly 100,000, but it's close enough. I mean, we're not going to be too upset. So this picture here shows the actual values that were drawn when I did a number of, or repeated the experiment a number of times. So I don't know if you can see it on the screen, but there's this big, really thin vertical line here. Those are the results from the Gaussian with a 0 standard deviation. So everything was 100,000 exactly. And then these red blocks here, this is with the standard deviation of 20. Any questions on this? Yeah.
The difference between a normal distribution and a Gaussian distribution?
The name. The question was, what's the difference between a normal distribution and a Gaussian distribution? And it's a different name. How I came across it?
Yeah, like how are we supposed to like see that in this problem? Yeah, trying to generate that.
Well, if you look at the plots which I apparently killed, so let me pull them up again. Uh-oh. All right, so I think the thing that you want to know about Gaussian distributions is that at the mean is the value that's the most probable. So its peak is at the mean. And so if you're taking 1,000 numbers from this distribution, then if you know which number you're expecting to see with the highest probability, and I'm not sure if the sentence is grammatical anymore. What it's going to affect is it's going to tell you that, like, if you have a standard deviation of 10 versus 20, it's just going to tell you what the spread of the curve is, but it's not going to change the expected value. So why don't I actually demonstrate that? Because I'm a fan of visuals and not necessarily good at English tonight. All right, so all I did in the code was I just changed the standard deviation of the first distribution to be 10 versus 20. And what you can see from the plots are that the value with the highest probability is still centered at 100,000. But the first plot, as opposed to the first time I ran this with 0 standard deviation, is a little bit more spread out. And the plot with 20 for the standard deviation is even more spread out than it. But they both have the highest probability at 100,000, or centered at 100,000.
So if you had a mean for G1 of 100, but a mean for G2 of 200, then you would expect 100,000
Yeah.
for G2.
So if instead you had a mean of, say, 200 for the second distribution versus 100, you'd expect them in two completely separate places. And you'd get an expected value that's 100,000 versus 200,000. So here, close to 100,000, close to 200,000, and then you see my distributions. All right, we good on this? Okay. So moving on. Question 4. What is the probability of the final value of num6 being 0? 9 over 10, the whole thing to the 10th power, right?
Yeah.
Okay. So does anyone not see why that's the case? All right, so I'm going to explain it anyway. So what this code is doing is, for 10 times, it's drawing an integer from 0 to 9, a random integer. It's a uniform distribution. And it's counting the number of times that the integer drawn is 6. And it's incrementing a counter. So the question can be rephrased as, what's the probability that no 6s were drawn 10 times out of a pool of 10 integers? And the way you can figure it out is on one pool where I'll say I have a 10-sided dice. On one roll, what's the probability of not getting a 6? It's going to be 9 over 10, right? And then if you do that 10 times, 9 over 10 times 9 over 10 times 9 over 10, that gives you 9 over 10 to the 10th power. And because this is a code class, sort of, we have a demonstration. So here's the, the answer that we hand jammed, or that we, just discussed. And now here's a function, count of 6. And it's the code that you see in problem 4. And all I'm going to do is I'm going to run a number of trials, and I'm going to count the number of trials that come up 0 and increment to count num zeros. And then I'm going to say this is what I think the probability of getting a 0 is. And then we'll compare the two numbers. Okay, so that's the probability that we count 9/10 to the 10th power. And then this is the estimated probability that we got from running this function 100,000 times. So, we good on this problem?
Instead of solving it the way that you guys solved it, can you solve it by saying the problem is also that it's 1 minus the probability that 6 will always be picked?
That you will see at least 1 6. 1 minus times the probability, or 1 minus the probability that you'll see at least 1 6.
No, never mind.
I mean, you can solve it in different ways. It's just that this way is, I think probably, or this way of thinking about it is probably more intuitive.
Yeah, when would you want to solve this kind of problem with, like, instead of when it says it's not something, to use 1 minus the probability that it is?
Well, my answer would be when it makes sense to you. Some problems are easier viewed in the negative light, which is what you're saying is 1 minus whatever. And some problems are better solved just in a straightforward fashion. So it's whatever tool gets the job done. And I mean, I don't have a general rule of thumb for you.
It's okay.
Maybe there's a course 18 person who does.
For this problem, would we possibly be asked, like, what is the probability that it'll end up being 1? Where it doesn't necessarily matter which of those 10 came out 6.
In this,
And how would you show that if we were going to be asked that question?
well, one, I haven't seen the quiz, so I can't give you a definite. But you could be asked, what's the instead of using 6, maybe say 1. Is that going to really change anything?
No, I guess I meant that one of those 10 outcomes ends up being a 6.
Right.
I can do it if, they say the 5th trial is a 6,
Okay.
but just one of those 10 trials being a 6. I don't know how to write.
So what's the probability that you get one of the trials is exactly 6? Or
Yeah.
exactly one of the trials comes up with 6?
Yeah.
Well, I think one way of thinking of it is, so we calculated 9/10. That's the probability that 6 doesn't come up. Right? So what's the probability that 6 will come up? 1/10. So instead of doing 9/10 to the 10th power, it'd be 9/10 to the 9th power times 1/10, right?
Okay, that'll count for any score.
So,
Okay.
and because I'm never very comfortable with this stuff, why don't we do a simulation? All right, so this is what we're saying, right? Exactly 1 6 comes up. And I'm going to set this to 1, right?
Isn't that saying that it's less likely that 1 6 comes up than 0 6s come up?
Mm-hmm.
Is it? Yes. That's true.
Yeah, because you're looking for you're looking for a sequence of 10 events where exactly one of those events is a 6, which seems more unlikely than, say, getting, everything that's not a 6.
Okay.
So, but, I want to verify this.
Why does it matter
because we're asking, if I roll this 10-sided dice 10 times, what's the probability that exactly one of those rolls is going to come up with 6, right? And so what we're asking is, what is the probability that I roll the dice 9 times and it doesn't come up with 6? And then what's the probability that on, on the remaining roll that it comes up with 6? Which is 1/10. So let's see if I'm, in the ballpark. Did I make a mistake?
I think it's like 10 choose one kind of thing, where there's 10 different ways that, so it would be like.
Oh, yeah. So yeah, you're right. See, that's why I don't like this stuff. So yeah, it's a little bit more complicated than that.
You only counted like one case of getting.
That's right.
Yeah.
So I'm only counting one case. There's multiple ways that exactly one dice could come up 6. So the answer is more complicated.
So when you just multiply by 10, because there's 10 different places, so.
Yeah, so actually that's what we got. So we'll just do this. All right? Well, of course it's going to come up, but the simulation gives us the same answer as what we've just kind of come up with discussing, right? So, okay, problem solved. Did that work?
Yeah.
Okay. Yeah, probability can be tricky.
So essentially, you could just take the probability that 9 of the rolls are for 6 and leave it at that, because you multiply it by 10 and 1/10.
Yeah, you can also do it that way. So yeah, there's multiple ways to think about the problem. So she was saying, instead of multiplying by 10, we just say that we take the probability that, we have 9 rolls that aren't 6. And that works too. That's what she just pointed out. So these parts cancel each other out. So it's basically, it is the same thing as this. Yay. All right, are we good on this question? All right. All right, problem 5. It was matching plots. So you have 3 functions here. You have a polynomial, or 2 polynomials. One's a cubic, one's a quintet, and one's an exponential, right? There are a couple ways that you could go about solving this one. One is to plug values in and kind of match them up with the plots. Another is to look at the axis of the plots. So this exponential function here, if we were to have it on 2 linear axes, the x-axis and the y-axis were both linear, you'd see the expected curve upward sharply. But if you notice, a couple of the plots are on a semilog y-axis. So if you put an exponential with a linear x-axis and a logarithmic y-axis, what would you expect the plot to look like? It'd be a straight line, right? So what that tells us is that if we look at the bottom plot, we have something with a straight line. So bottom plot is the 3rd function, right? It's exponential. And then for the remaining 2 functions, there are a couple methods that you would use, or you could use. One is to plug values in and see where the plots wind up, or see where the points wind up, and compare them with the plots. Another way to think about it is that one of the plots is on a semilog, and another plot is on just both linear axes. And if you plot a polynomial, and that's not exponential, on a logarithmic y-axis, what would you expect the curve to look like? It should look like, somewhat similar to a logarithm, right? So with that in mind, you could then start plugging points in And what you would come up with is that the second function is this top plot here. And the middle plot here is the first function. Is there anyone who's lost on that? Uh-oh.
Wait, why? So you have two quadratic functions, right? One and two are quadratic.
The polynomials are not exponential.
Okay, and then the third one's exponential.
Mhm.
And the reason why the third one's linear is because they plot an exponential on it.
If you plot an exponential on a logarithm with a linear x-axis and a logarithmic y-axis, it should be a straight line, right? Or straightish.
Why?
Just the way the math works out.
Okay. I'll think about this later.
Any other questions? All right, we'll move on to the next one. All right, what does the following code print?
And then square root side 3, square root side
Close. So I don't actually have the answer. Well, it's not written down. But I have the code, so I'm just going to run the code. So you're close. Should we spend some time stepping through this code, understanding it? All right. So what question 6 does is it creates a class hierarchy. And at the top of it, it has the shape class, which has just two methods, double underbar EQ and double underbar GE. Those just define the equals operator and the greater than or equal operator for shapes in terms of their area. So what this is saying is that two shapes are equal if their areas are equal, and a shape S1 is going to be larger than another shape if its area is larger than the other shape. So like if I had like well, let's go down and we'll get to that in a second. Square, subclass of shape, it is what it says it is. It's a square, and it has a side, and its area is what you would expect it to be, the side squared. And circle is just defined, it just has a radius, and its area is what you would expect it to be. Okay? There is a function here, f, and it takes a parameter L. And L, if you look at the code here and you kind of walk through it, L would have to be either a list or a tuple of elements, right? Doesn't necessarily have to be shapes. But this first line is just going to return none if the list is empty. And then these next lines are going to, it's going to set the first element equal to x, and then iterate through each element in L. And then if the element it's looking at is larger than x, it's going to set x to the element. So what this function is doing is finding the largest element in the list, right? Everyone follow that? Okay. So this should be pretty straightforward, as should this. This part might trip some people up. So this obviously creates an empty list. What this does is it creates a dictionary of class names. And what it's saying is that for a key of 0, the class is circle, and for a key of 1, the class is square. Does everyone see that? Okay. This loop here iterates for 10 times, and it appends 10 elements. And then each of those elements are defined by this shapes dictionary, right? on each iteration, it's going to take the modulus of I, the index, or of the number, and if it's a 0, it's going to construct whatever class the dictionary shapes returns. So if it's an even number, it's going to be a circle, and then if it's an odd number, it's going to be a square. Everyone follow that? Does no one follow that? Okay. Or does anyone not follow that? Got my logic messed up. All right, so now what we have here is a list of shapes. And then all this does is it's going to print which shape. Is it going to be the 4th or the 5th shape? 5th, right? Because we start indexing at 0. So this number is obviously even, right? So this should be a circle shape, or a circle class. And what should its radius be? Right. And then this line here is just going to call the function f, which is going to find the largest shape, which is determined by its area. And in this particular instance, it's going to be circle with radius 8. So once you figure out what f does, this is actually not such a hard problem. So the key to understanding this one is figuring out what f is actually doing. And it's purposely, you'll probably see a problem or two on the exam that's written like this, where the function has been obfuscated. So it doesn't have nice little variable names. You know, if we were writing this for real, it would be like something like that.
Wait, what was the radius on L? It was,
Radius on L?
not radius, what was, like L4 was, it was circle, and it was that all it was? It was just circle?
With radius 4.
With radius 4, okay, that's what I thought.
Yeah. All right.
How many of those special underbar functions have you seen? Like have you seen anything besides image, string, and the residential thing?
So how many of the double underbar functions have you seen? It's a good question. You've seen a lot, right? The ones that I would be familiar with, definitely init, definitely EQ, GE, and definitely STR. You might want to be familiar with this, LE. So what does LE, what do you think that does? Less than or equal to. Less than, so it's the opposite of GE, right? I think there's also LT, so less than, and GT. So it's fairly logical. And historically, you don't need to have these memorized. Like, I don't think I've never seen a question where you've actually had to produce code that uses double underbar on the quiz. You just have to understand what it's doing if you do see it, like in a code reading exercise. Right? And the conventions are fairly straightforward to understand. All right, can I move on?
Can you scroll down a little bit?
Yeah.
Where it says print L4 and I guess print FL. Why does does it automatically just print the string function?
Yes.
GR?
So you're asking why I don't have this.
Right.
Right. So in this flavor of Python, and if you don't have an explicit conversion to string, Python will look for the underbar str function if it exists. If it doesn't exist, then you get that weird object at blah, blah, blah. Okay. Any other questions?
What list are you feeding into FL?
Are you confused because it's the same name?
Maybe. I don't know, because like, so the third thing that comes out is like, I understand the second thing, the circle with radius 4, but like, how do you get circle with radius 8?
Well, the way we get that is f of L, I mean, f is a function, right?
Right, and
What-
radius is the largest element of the list.
Right.
And the list L contains 0 to 9.
Yeah, so I mean, we can actually print out what L contains.
Why isn't it squared? Isn't 9 odd?
Well, why don't we do it? All right, so all this is going to do is it's going to print out all the shapes in the list and their areas. Oh yeah, I've got stuff at the top. Okay. So this is the first shape, and then as we move down the list, you know, we have square with side 1, circle with radius 2, 3, et cetera, et cetera, et cetera. And then this is the area of the circle with radius 8 versus the area of a square with side 9. So, and it depends on, the reason why it works this way is that this greater than or equal to operator is defined in terms of the area method of the shapes. Does that?
So wait, what is it doing then? L is a list of areas?
No, L is a list of shapes.
Okay,
So,
but,
well, it's a list of subclasses of shapes, right?
and so you're being F, this list of shapes.
Mm-hmm.
Oh, and to compare if S an element of that list is greater than or equal to X, you have to use the greater than or equal to
Operator.
method
Right.
in class shapes,
Yep.
which compares areas.
Mhm.
Okay.
Now, I might regret this. I think this will work. Yep, it works. So you see this weirdness I have here? It's showing pretty explicitly that I'm calling this GE operator, right? It's just, so this is really just shorthand for that. Syntactic sugar. It's easier to look at, easier to understand. And to even drive that point further home, whenever that comparison is done, it's going to print out I am here. So it is actually getting called. I'm not just blowing smoke. Okay. Have we beat this problem to death?
Yes.
All right. Last problem. So I'm actually not a huge fan of this problem, but the way I think of it is it's the number guessing game, right? So I say to you, I'm thinking of a number between 0 and 100, or in this case, max val. And your job is to guess as quickly as possible what number I'm thinking of. The only thing I can tell you is that you give me a guess, and I'll tell you if it's higher or lower, or if it is the answer, right? So if I am thinking of a number between 0 and 100, what's the strategy?
Section half.
Well, binary search.
Or binary search it.
Binary search, right? So you're gonna start in the middle. You're gonna start at 50. And you're gonna say, I'm gonna say, well, no, it's the number I'm thinking of is lower, right? So now you're gonna guess between 0 and 50, 25. I'm gonna say, well, it's higher, right? Now you're gonna guess between 25 and 50. I don't know, I didn't actually think of a number, but you get the idea, right? So this problem is asking you to implement binary search, all right? And comp guess here is functioning as me in this problem, right? It knows a number, and you write the program that's going to guess it, which is find number. So there are multiple ways to do this problem. Here is my solution. All right. This is just an implementation of comp guess. Right? At the beginning, I set a maximum value of 100,000, and I'm going to guess a magic number, or I'm going to choose a random number from between. Yeah.
When you say binary search, is that the same thing as bisection search?
It's the same idea, but the way that I differentiate binary search from bisection search is that you do a binary search on a finite list of elements, of sorted elements, right? So I might have a list of names in alphabetical order, or a list of numbers in ascending order, and I would do a binary search on that list. With bisection search, it's not necessarily a finite list of numbers or elements that I'm looking at. I know that the answer exists within a lower and a higher upper bound, and I'm going to divide that search space in half successively or iteratively to find that actual value. But it's not necessarily a finite list of elements between those bounds. Yeah. That's good?
Yeah, makes sense.
All right. So this is one implementation. You can do it any number of ways. This num steps thing, you wouldn't need to have. It's just, for me to illustrate some stuff. So I'm going to start at 0, and I'm going to start at max val, and then I'm going to keep iterating while I haven't reached the answer, basically. So I'm going to make my guess in the middle, and then if comp guess tells me that it's higher, or that my guess is too low, basically, then I'm going to set my my guess is too high. Then I'm going to set my upper bound to my guess, and then I'm going to search in the middle from there. And then if it tells me that my guess is too high, then I'm going to search in the upper region. Otherwise, that means that I made the correct guess, and I'm done, right? So pretty simple. The key part of this problem that tells you that you should use binary search, though, is that it stipulates you need to have a log max val algorithm, right? And binary search is a log n algorithm. I mean, you could do find number in a linear search, but it would be fairly inefficient. All right.
Just like guess one number and then go.
Yeah,
like
start at 0.
Guess 1, and then guess 2, and then guess 3.
Yep.
Okay.
So you just keep incrementing by 1.
Yeah.
If it didn't,
What's that?
if it didn't specify, like, it should run in, like, log and time, would it be okay if we had used the linear search?
If it didn't specify the complexity, then yeah, you could use whatever search you deemed appropriate.
Okay.
But because it said it needs to be log in.
Yeah, okay.
Are you running like
What's that?
Are you gonna run like
Not in this particular case. So, because we're dealing with integers anyway. So, all these operations are going to result in integer results.
Wait, are you gonna ever be able to get the highest number?
So if it were like 900 or 99,000, is that what you're asking?
Number with max value.
If the number were maxed out. Well, let's see. I might have a bug in my implementation. Always possible. If I do, I'd probably take 1 point off me. Yeah, so I have a bug. So I am actually... Yeah, so I have a bug. And, I'm not going to try and fix it right now. But yeah, if I were grading this and this were my solution, I'd dock me a point or two.
What's your error?
My error is that because of this, the way that I get my guess here, I'm never going to get to max val. Like I'm always gonna, like if the computer chose max val as its guess, then I'd never get to that. So, yeah, you caught me.
A friend of mine looked at this and was like, oh, you should define another function to solve it. Is that kind of thing actually allowed on the exam at all or not?
Well, why did your friend think you would define another function?
I'm not exactly sure.
Okay.
It was supposed to be like define,
Is he saying define a recursive function?
I think that's what I was trying to do.
Yeah. So I'm solving it iteratively here. You can write a recursive function. And in this case, because we've given you the specification for find number, you would probably write something like find number helper and have whatever additional parameters you needed in order to support the recursion.
So you can do that or not?
Yeah, we'd be fine with that. The point is that you write a function that runs in log max val time.
Because at the top it says that the magic number is in range, maxed out, doesn't that mean that the number would not ever be maxed out?
Let me see. Actually, yeah.
So you're correct.
Because it would be 0 to 999.
Yeah.
Or 99,999. So, well, no, I'm not sure if this actually constitutes a bug or not. So I'd have to do further testing. I don't have any test cases set up, which is, again, back to unit testing. Do you have a question or?
Yeah. Could you do this by saying your guess equals choose a random number between high and low?
You could, but it would have, analyzing the complexity would be problematic, I would think. This, doing it this way, be guessing right in the middle, it's going to be log maxed out complexity. If you were to choose a random number between low and high, I'm not sure what that would do to the complexity. It would make the analysis a little bit more intricate. So, and if you did that if this were the actual quiz and you put that as your answer, we'd probably take a fair number of points off for it. So, there are people who do study algorithms that do that though. They use random numbers in order to compute the values. All right, so we're done with the quiz. And now we've got a list of topics to go over. So let's start at the top. The first subject that was listed, so all of you got the list of quiz topics for the quiz, I'm assuming? Did all of you look at it? Okay. The first topic is algorithms. And I have big O notation, exhaustive enumeration, guess and check, successive approximation, divide and conquer, binary search, merge sort, hashing, orders of growth, and amortized analysis. So first come, first serve. What do people want to see?
Yeah, hashing and amortized analysis.
Hashing and amortized analysis. Okay. So why don't we start with hashing, because that's pretty easy. The idea behind hashing is that you have a function, and it's going to take some input, and it's going to compute an address of some sort. And let's imagine that I have a data structure that has a number of buckets arranged one after the other. What hashing does is it says, I have this input S, or a key, if you will, and I'm going to compute an address, like a number of some sort, and it's going to say wind up here. And this relates to Python because this is how dictionaries are implemented. So this S here is going to be the key that you give the dictionary, and then it'll compute a location for this bucket where it's going to put the value. All right? So the idea, what makes these hashing functions valuable, especially with respect to dictionaries, is that you can check for the presence of a key or a value in constant time, because the hashing function is more or less constant, and once you have an address into the data structure, it's very easy to compute the location where you're going to put something. So I'm not, does that kind of help you? You're not going to have to know, you don't need to know hashing in great detail. Like, you're not going to need to know the hashing function for like a string, or the hashing function for a tuple or something like that. The main points that you need to get from hashing is that it computes an address into this data structure. It's a constant time thing, and that's about it, actually. If you have those two concepts down, well, also three, that's how dictionaries are implemented. If you have those in your mind for hashing, you'll be good. Does anyone have any other questions for hashing?
So we never have to like write a hashing function. It's more just like this is.
Right. This is so that you know what it is, and when you see it in the future, if you see it in the future, you're not totally lost. Like, you have an idea of what it's doing. You can define your own hash functions, but we're not going to require that of you in this course. Okay. All right, so that's hashing basically, and all you need to know for the quiz. So for amortized analysis, the idea behind amortized analysis is that you have maybe you have a known kind of sequence of operations, and you might have you're trying to find what the worst case runtime for that sequence of operations is. And you might have a bunch of operations that are really, really low cost or low complexity, and one really expensive one. And for our purposes, we're trying to find this, find which of these operations is a dominating factor for the complexity. So the example I would use is, let's say that I have the task of searching for an element in a list of, big list of elements, right? So we know two basic search algorithms for this, right? We know like a linear search, where we go one at a time through each of the elements, and what's the complexity of that? What's that?
Just like the length of what you're...
It's going to be linear in terms of the number of elements in the list. We also know binary search. Now, what's the complexity of binary search? Log n. Now, there's a problem with binary search. It has a requirement. Will binary search work on a list that is not sorted? No. You require it to be sorted. So, we've talked about sorting in class, or he covered it during lecture, right? For basic sorting that we've seen, the lower bound, or the complexity of the sorting algorithms is n log n, right? So like merge sort will be an n log n algorithm. So let's say that we just need to do one search, right? do I want to necessarily, do I really want to use binary search? Why? Because I have to sort it first. And if I just do, if I do, I have to sort and then search. And this is going to be whereas if I do a linear search, I just have search. Right? And for just a single search, for binary search, this is going to dominate my complexity. But let's say that I'm going to do 1 million searches, right? Now, it might behoove me to actually sort this first, because I only have to sort the list once, and then I can do as many searches as I want. So, in the grand scheme of things, if I'm doing 1 million searches, then linear search is a really poor choice, and binary search would be my best option. And this is about as deep as we want to go with amortized analysis. It's this idea that there's a certain point at which one algorithm becomes more important than another algorithm because the composition of its operations kind of determines, it kind of changes as you increase the number of elements you're working with, or the number of times you're going to do the operation, right? So that's kind of what you need to understand for amortized analysis. And it can be used in other types of analyses, but we're not going to get into that. Okay. All right. What other topics do we want to go over for algorithms? We've got big O notation, exhaustive enumeration, divide and conquer, successive approximation, merge sort, and orders of growth.
We go over merge sort.
What, you want to go over merge sort?
Yeah.
Okay. So, and today I actually have my code. So, merge sort is a divide and conquer algorithm. And the idea is that I am going to take a list of elements and I am going to divide the list in half. So I'm going to get a left list and a right list, and they're unsorted. And then I'm going to call merge sort on that. And I'm going to keep recursively calling merge sort until I have one element or no elements in the list. And then I'm going to return the list. After I do a merge sort on the left and right halves, I'm going to merge them. And the merge operation is just going to start at the beginning of the left and right halves of the list, and it's going to append the smaller element at the beginning of each of the lists to result until it gets to the end of the lists. So I'll try a Blackboard demonstration in a second, or explanation in a second. So this before parameter, all this is doing is it's determining the order of the elements. So it's saying that left should come before right. Right. It'll return true if left should come before right, and false if right should come before left. So intuitively, because I don't think that was a very good explanation. Let's say that I have a list of elements. and are unsorted. What am I missing? All right, so it's an unsorted list of elements. When merge sort first starts, it's going to divide this list into left and right halves. So basically, it's going to take the middle here. And then it's going to call itself on this left half, and then on this right half. And it's going to keep doing this. It's going to divide this half into, say, 5, 2, 1, yeah. Now, when it gets to these little single elements, it's going to do something interesting. It's going to merge these two. So when it gets down to these single elements, it's just going to return the list as is. It's not going to do anything to them. And then the code after this division is going to merge them. And the way it merges them is it's going to start at the beginning of these two lists. And it's going to say, is this element larger or smaller than this element? Or is it going to come before this element? And it's going to construct a merged list. All right? And then return that as its result. All right, so this is going to come down. So now, at this point, it's popping back up the stack. It's going to return this. It's going to merge these two lists. Starts at the beginning of both lists. 1 comes before 2. And then this list is done, so now it only has this list to do. After each merge step, these lists are going to be sorted. So now where are we at? So now let's do this guy. So this guy gets merged into 6 and 9. And then this guy, I didn't divide up, so bad on me. All right, so we're going to merge those two single element lists. Now, these get merged. So these guys are going to get merged. So this is going to become, I think my tree got messed up a little bit. Now we're going to merge these lists, right? So we're going to start at the beginning. 1 comes before 3. First element is 1. 2 comes before 3. Now we're here in this list. We're still at the beginning of this list. 3 comes before 5. 5 comes before 7. And we're here. 6 comes before 7. Then we have 7. And then 9 comes before 10. Now we're done with this list. So now we have 10, 13. And at the end of the last merge, the list is sorted. So I'm not sure how clear that was.
What happens if there's a number in the list to like all of yours split equally into individual elements, but like what if there's one more element at the top? Then it would just split. You know what I mean? If there would be one under.
What do you mean? So, like, there's an odd number of elements in the list. So, you would just get an uneven split. So, you know, your left sublist might have 6 elements. Like, say you have 11 elements in the list, left element would have 6, or left list would have 6 elements, and then the right list would have 5.
Okay, and then that would split into 3 and 2.
Yeah.
And then the 2 would split in 1 and 1, the 3 would split into 1 and 2, and then the 2 would split again.
Mm-hmm. And then the 1 would actually make a call, but it would be an empty list. So, it would split, but one of them would be an empty list.
Oh, okay. So then it would just get.
Yeah, I mean, that's kind of what happened with my tree. I didn't go all the way down on some of the branches of the tree. So, but the idea is that, I mean, the main idea behind merge sort is that you split the list in half, whatever size it is, and then you merge sort those separate halves. And merge sort's going to do the same thing with those separate halves. It's going to split them in half and sort those halves until it gets to the smallest case, which is an empty list or just a single element. And then it's just going to start merging these lists.
Right, I was just wondering what happened once you got down to 3.
Oh, yeah, you split it into like 2 and 1, and then that merge sort would be like 1 and 1, and then this one would split it into a list of 1 and nothing.
Okay.
That's all. And then the merge between that's obvious, right?
So in the merge sort lecture notes, at one point lambda is used. Can you explain a bit like how this works?
Did he actually use lambda?
Yeah. Well, it isn't useful. I guess the worries about it.
Use lambda. Okay. Python has these functions called lambda functions, and what they are essentially like one-liner bits of code that return a value. So, let's see. How would I can't believe he used lambda. I'm trying to think of where I would actually use them. Like an example, and I don't have one off the top of my head. You're not going to see lambda on the quiz. The syntax is not too difficult. It's basically, it's like lambda x, and then it's going to return like x squared, right? This is going to create a function. And it can be something like, I assign this lambda function to a variable square, and I'm going to pull up a separate. So I'm creating a function square, but instead of writing something like this, I write it as this, and what's that?
You have to save it before it lets you run it.
Yeah, no, that's again what I'm just trying to think of a witty name. I'm actually stunned that he whipped lambda out in lecture. So really, it's a way of defining these one-liner functions. Python's lambda functions are kind of broken, at least in the 2.5, 2.6, 2.7, like 2.x versions. 3.0 or 3.x versions of Python, I think, actually do away with lambda because they were broken. You find lambda functions in a lot of other programming languages like Lisp or Scheme. And you're never going to see those on a quiz. But if you want to learn more about them, you can look it up online. So.
Well, you're running the function. What is
Here.
the same thing? Oh, okay.
Yeah. you know, I had it there as an illustration that the functions are functional, they're functionally equivalent. And it actually serves to illustrate another point that functions are, you know, objects, and you can assign them and pass them around and stuff. But lambda functions on their own, you're not going to need to know that piece of linguistic Pythonese, or bad sentence. You're not going to need to know it. Does that work? Okay. I'm going to have to ask him about that, because I can't believe he used it. Lambda in lecture. Okay.
In one of the lecture notes, he used something called X-range.
X-range.
What does that do?
Did you talk about generator objects or iterate or yield? You haven't seen those? Okay. So what you're asking is something like that. He used something like that, right? The difference between range and X-range is that range returns a list of integers, and X-range returns a generator object. And I know that really meant a whole lot to you. So let's say that I assign. Yeah, that's what I'm going to show. So if I do print list of integers, right, or list of numbers, it's actually going to print the list of members. Someone fall back there? So it's actually going to print that list, right? Now, if I do something like pretty sure this is not going to print a, yeah. The reason is that if you look at the type of the object that's returned, it's telling, well, X-range doesn't really help much either. Damn, why does he do this to me? It's a way of, so let's say that you have a list of 1 billion elements or numbers or things that you need to iterate over in a for loop. It's probably not a good idea to bring all of those into memory at once. So, or to necessarily keep them all around. You want, that's where things like X-range come in. So let's do this.
X-range 10, print I is just going to print 0, 1, 2.
Yeah, so if I do this, it's going to be the same as if I were to do this. All right, it's gonna have the same functional effect, but the difference comes in, let's say that I were to do something like this. A lot of numbers, right? I'm hoping Python crashes on this because this is my whole point. Yeah, so there's too many items. But let's see if I do it with X-range. Well, I should probably comment this out. I chose a really too large number, didn't I? Well, I want to find a number that has too many list elements, but Python can still feel comfortable constructing an X range out of. The point is that there's a certain point, a certain number, well, it's going to do that comfortably. So you see this little delay that's occurring? Actually, it's kind of long delay. It's actually hanging up on this range command because it's actually constructing this list object with all these integers in it. So let's say do this. Are you going to need to know the exact difference? No. Is there a difference? Yes. Am I prepared to explain it exactly right now? Not really. Previous iterations of this class have covered the yield statement in Python, which allows you to create functions that create generator objects that you did yield? All right, well then you should know about this. So range is going to give you a list of integers. XRange is going to give you a generator object that uses yield to produce these integers. All right, so let me see if I can rescue my machine. All right. Okay. So he covered something like that with yield. All right. So if I were to say do I in my X range, back to where I was. My X range does the exact same thing that X range does. All right. Now, as I said before, if I do a list, or if I do range, that's going to be a list, right? If I assign this to see that? That's what the yield statement does for you. It produces that generator, and that's how XRange functions. So basically, it allows you to do some interesting things. Like in this case, it's not too interesting because it's just returning a list of, or it's just returning one integer after the other. But let's say that I wanted to do def my squares. All that's going to do is return the squares of all the numbers between 0 and max n. Right, so if I were to do this, it should print out all the squares, or all the squares of all the numbers between 0 and 9. Make sense? So that's what yield gets you. Those are generator objects, and that's how XRange works. That's how it's different than range, right? Does that make sense to everyone? Okay, I don't need to beat that to death any longer? All right. I was not expecting that question. Okay. What should we go over next? Is everyone comfortable with orders of growth? Okay. All right. The next major topic area I have is linguistic issues. So this covers stuff like exceptions, polymorphism, classes, and objects. So people want to go over classes, objects, polymorphism? Okay.
What's polymorphism?
Yeah, we'll get to that.
Sorry.
It's all right. So before my computer crashed. All right. So here are some class definitions, right? So I have a shape object, and I've defined two methods, area and perimeter. They currently do nothing except for raise not implemented errors. And now I've defined a class hierarchy. I have a rectangle class that inherits from shape. All right, so shape is a superclass of rectangle. Rectangle is a subclass of shape. This also says, well, let me ask the question. Is shape a rectangle? It's not rhetorical.
Not necessarily. No.
Not necessarily. Is rectangle a shape?
Yes.
Okay. It's an easy question. It's not a trick question. All right. In the rectangle class, I have an init method. It just takes a length and a width. So computing the area is really easy. And then computing the perimeter is also very easy. And now I have a string representation, which is just rectangle with the length and the width. Ellipse inherits from shape, and it has one radius, or one, the long axis and the short axis, right? And computing the area for that is pretty easy. Computing the perimeter, on the other hand, I had to look it up online. So if you're interested in the formula I used, go take a look at this website. Again, I have a string method, and then now we have a square, which inherits from rectangle, because square is just a special case of a rectangle. And so I'm going to reuse it. I'm just going to make both lengths the same, right? That makes sense to everyone? Okay. Then I don't need to override the area perimeter because they're pretty easy to understand, or they're the same. And then circle. It just inherits from ellipse, and same thing. I'm just going to reuse the stuff that I have in ellipse. And all right. I've defined a bag of shapes here. Circles, squares, rectangles, lots of stuff. Now, to answer your question, what polymorphism allows me to do is it allows me to treat subclasses that share a particular superclass or a parent class the same. So I've defined an area method on the shape class, right? And all of my subclasses, rectangle, ellipse, circle, and square, inherit from this superclass. And some of them override area, some of them don't. It doesn't really matter to me. It's just what matters to me is that if I have a bag of these shapes, I know that I have an area method. And I don't need to know the particular or the type of the object that I'm calling the area method on. Right? Python is going to take care of that for me. I can just iterate through this bag of shapes, call the area method, and I can get some of the areas. So, I mean, that's what polymorphism gives to me, is it allows me to treat objects uniformly. It allows the objects to change their behavior based on the particular type of object that I'm using, but I don't need to know the particular details. So it's pretty powerful. So it's like, you know, if I were to create a racing game and I wanted to drive a car, you know, I could have different models of car, but I wouldn't, you know, my game engine wouldn't need to know like the drive method to call for like, you know, model you know, a Ford car versus a Chevrolet, all that stuff. So, that kind of answer your question? Yeah. All right. So, yeah.
So if there's not a area function that overrides it, what is it going to sum if it just raises a non-implemented error?
Well, in this,
yeah, if you haven't redefined.
yeah, in this example, I'm using all what are known as concrete classes, so they're not abstract. They all have implementations of area, right? But if I were to say, I don't know, for some reason I decided that I wanted to make something amorphous, right? This should raise an error, right? Unless I have invalid syntax. Oh. All right, so when it gets there, yeah. Any other questions on this one? They're related, but what inheritance means is that if I say that rectangle inherits from shape, that means it gets all of its methods and attributes. But it's not necessarily polymorphic in that case. It's just, it's like it's saying a rectangle is a shape, so it has all these characteristics of a shape and then some, right? The polymorphism comes in when I override the area method, and then I can treat like all shapes, whether they're rectangles, squares, circles, uniformly with the area method. Like, you know, you might, I'm trying to think of an example where it would be. So let's say that I didn't do this in a class-oriented way or using classes, and so I had a really, I don't know, naive implementation that said, let's represent them as dictionaries, right? Okay, so I have two really stupid functions here. And all they say they make a circle and they make a square. And so really all it's doing is representing these as dictionaries. And the key is side and radius. Now, let's say that I want to have my list of shapes. I'll make a square, I'll make a circle. Another square. Okay, so now I've got a bag of shapes, or a list of shapes, right? What's that? Oh. Spending too much time on that one. All right, so if I were to take a look at this, all right, it's going to print out a bunch of dictionaries. Now, the question is, what if I wanted to compute the areas of these data types, right? Using polymorphism, I can just call .area on each shape, right? But if I wanted to do the same thing with this code, I would have to have like square area S, return D, side. Right, and then def circle area C return 3.1419 times C. Oh wait, I'm already getting tripped up. Okay, so even this is not so bad, because if I, do something like this, I can still get the areas, right? And I can do this because I know what's in those positions in the list. So, oh. Okay, so it's going to work. But now, if I want to print out all the areas of all the shapes in this loop here, how am I going to do that? Because I can't just call, square area of S, because what if S is a circle? It's going to give me a bug. It's going to give me an error, right? I could get around this by saying if radius in S, then I know it's a circle, right? Or side in S. But you see how the code's getting kind of ugly now? I have to know details about how these different objects are implemented, how square and circle are implemented in the dictionary. I have to know what type they are before I compute their area. And I can do it, but it's kind of ugly. Whereas if I invest a little bit of time in, go away. If I invest a little bit of time in a class hierarchy, I can do this much more easily, much more cleanly. It's a way of kind of abstracting from the problem. You don't have to worry about the details of the individual shapes. So, did I kill that and beat it into the ground?
Just for clarification, so the point of polymorphism is just like inheritance, essentially? Like, kind of boil it down,
The point of polymorphism is that, if you have a class hierarchy of objects, you don't need to know the details of the objects, or of what specific type an object is, as long as you know that they, like, in the case of,
there exists a method that you want to use.
right.
Inherits from that class.
Yeah.
You can use it.
Yeah, so like in this particular example, shape has an area method, and I have a bunch of concrete subclasses of shape that have all overridden the area method, and they do it in different ways, right? You compute the area differently for a rectangle versus an ellipse, right? I don't have to worry about which particular shape it is. I just call the area method. And I don't have to do all the checking that I do here, where I look at, is this a circle, is this a square? I don't know, so I'm going to compute it.
How do you avoid the checking in doing so?
So, see.
Oh, okay, great, yeah, okay.
Okay. Did I make it clear? All right. Anyone lost? Any other questions? Okay. So that actually touched on a couple of topics, right? So we saw exceptions here. Is there anyone who wants to see anything else on exceptions?
What's the difference between pass and continue?
Pass and continue? Okay. So the question is, what's the difference between pass and continue? So when you have pass, this is basically a null command. It's a do nothing command. I can actually run this code right now, and it will do absolutely nothing useful, but it also won't complain. Okay? It's a placeholder. Sometimes, so like a lot of times we'll see in your code something like this. Let's say x equal 150. If x mod 2 equals 0, pass else, do something useful. All right? So we see this a lot in your PSITs. It's not a slam on you or anything, but you can simplify this by saying but the way that you conceptualize the problem forced you to have this if statement, and then you didn't have anything useful to put in here, so you had to put a pass in order to make Python not complain. So let's be a little less flip and more concrete. It's getting late. I'm getting punchy. All right, so if I were to run this now, it's not going to print anything because it hit the pass command, right? Now let's make this odd. So we verified that this code works and that I'm not blowing smoke. Now, let's take out the pass. Python's going to complain. Why? Because after this if line here, it's expecting a block of code, but there's nothing there. The pass keyword gives you a do nothing command. It says, I don't really have anything to say here, but you want me to put something here, so I'm going to put something here. But it doesn't do anything. So that's passed. It's a placeholder. This is a basic answer. Now continue is different because continue actually has a function that is useful. Let's say that I'm not too familiar with the range command and I don't know that I can specify a step. And I want to print out all the odd integers. And I also am going to restrict myself and say that I can't use an else or something of that nature. So I'm gonna handicap myself. Is X range cool? All right. So I only want to print out odd numbers. Okay. Or we can do it like this. Either or, doesn't matter. So comment this. What continue does is if you're within a loop, as we are here with this for loop, it tells Python, if it sees a continue statement, do not continue beyond this point within the block of the loop. Go instead and perform the next iteration of this loop. Go to the top of this loop. All right. So what this code should do, I'm hoping in case I might have a bug, it should print out the odd integers. So what's happening is that when the integer is even, it's hitting this continue statement. And this is telling Python, go back up to the top of this for loop and do the next iteration.
If you would have pass instead of continue, just print it out.
So if I just had pass, it'll print all the integers. Does that work? Anyone confused?
You could also have your code, right? Like if not that, then print hash.
Yeah, but I need it in really quick. So. There are some schools of thought that say that continue is something that disturbs the flow of code and sometimes should be avoided. I don't subscribe to that. I think that if it makes your code clearer, then use it. Which is to say that, yeah, you can rewrite a lot of your code to not use continue. Okay, do we need to go over anything with linguistic issues? Are we good on class? Sorry.
Can we go over exceptions, please?
Okay, so there is a question of exceptions. So exceptions are another way of flow control, right? And if I can pull up my source file, I have an example of handling exceptions. There we go. All right. Exceptions give you a way of handling certain errors that occur, all right? So The easiest one to come up with is division by 0. So normally, if you would do a division by 0, so I'm going to try and divide 10 by 0, right? The universe won't end, but Python will be very unhappy, right? In kind of programs that are more complex than the ones that we've been writing, division by 0 happens, but you don't necessarily want the program to crash, right? You want to be able to handle that error in a semi-graceful way. And in this particular example, we can, with a division by 0, we can do that with exceptions. So let's say that instead of the program crashing, I wanted to print out a nicer error message. Rather than everything in big red, I say, well, you divided by 0, so maybe you should change your numbers. The way I capture or catch this exception is I have a try keyword, a colon, and then I have this block of code. This is the code that could potentially raise an exception where the error might occur. All right. This code could be, in this case, it's just straight up assignment and division. It could be a function that raises the exception. It doesn't matter. The point is that there's an exception that might occur. If an exception occurs, then Python is going to look past this block of code here at these except statements. And it's going to look at the type of exception it has. In this case, it's a zero division error, right? And it's going to match the exception against whatever type this is. And you can put inside here whatever code you want in order to handle this exception. So in this case, I'm just printing divided by 0. I could be rude, and I could, I don't know, say, see, can't even spell. All right, so I can handle this exception however I want, but the program's not going to crash, right? And this program's actually not going to really convince you of that, but you see that the first thing that you see here is that there's no big red blaring message that says you have an exception. It's all code that I've written, and I could even be silent about it. I could say, I'm not going to say anything. I'm just going to let them fail silently, right? And just tell me it's all good, right? It's not going to tell me I divided by 0. It can come in handy if I have an input loop. So let's say I'm going to do a little bit more, be a little bit more creative and do, that's an internal Python thing.
Oh.
So it's if you want to learn about all the wonderful exceptions that Python provides you in its class library, you can go to the Python documentation, or you could even, do a Google search. Of course, Chrome is being very slow and network's probably down. So built-in exceptions. So these are all the exceptions that Python has. And you can use these too. Let's say that, let me get back to my contrived example. I want to create a loop that says, let's say that I want to catch, I don't want to divide even numbers for some reason. I don't know. What do we have here? What can we find? I think there's a value error. There we go. So let's say that I'm going to raise a value error. Okay. And I am actually going to do this this way. So I've created a function that's not going to allow me to input even numbers, right? It's going to raise a value error if I enter in a 2 or 4 or whatever. But if I do enter in an odd number, it is just going to return that number to me. So I'm going to use that function now. And I'm just going to do the silly thing and do a division and print it out. All right. So if I comment out this code up here and I comment this out and I run this, so let's do 3. That's interesting. Apparently Python is a little constipated right now. We edit this during the summer, so we can take that out, I think. All right, so it does what we expect it to do. It's going to keep prompting us for numbers, and it's going to divide them for us and give us the answers, right? So we've got a really dumb calculator here. Except when I hit, try to do even numbers, because my calculator is really, really dumb. All right, so it's going to raise a value error. And it raised the value error in this function here. I can handle this, though, because I know how. So, what should I type here? Okay.
I mean, if you wanted to specifically catch that error, but you could just leave it as except, right, and it would catch any error?
Yes, we can. So,
If any error were to be thrown,
yeah.
then
But-
this. But if you wanted specifically to say, all right, if value error is thrown, I'm going to use this to do this.
Right, and I mean, so what she was saying is that I could do this. I don't have to specify what error I'm expecting. I could say, but it's not really going to give me any detail about what happened, right? And what I'm going to do is I'm going to say that if I had, okay, you're stretching. If I have an exception, then I'm just going to, repeat my getting of the numbers, okay? So let's say that I do this. Hey, something happened. Not really specific. Hey, nothing happened. Okay, I divided, all right. So,
What if you put in man?
what's that?
During man, would it also come back and hey, something happened?
Yeah, that's a good question. Yeah, something happened, but we don't know what, right? Like, we know we have a bug because an exception was thrown, but we don't know what
It's
it
never
is.
going to crash.
Yeah, it's never going to crash.
So like, what a useful example of like when to use this is would that be like when we were making Hangman back in the day, and you had the list to choose from the letters.
Yep.
We had to pick the letters, and then it would remove each of the guesses.
Uh-huh.
If you accidentally guess something that you've already guessed,
Yeah, you can raise an exception and say, already guessed
as
this.
opposed to the program. At first, when I ran it, I accidentally hit the same letter again,
Yep.
and the whole program just crashed.
Yep.
So you raise exception for like whoever's playing has really bad memory or
Yeah, and you could catch any errors that are raised. So like, you've got a couple of exceptions that are raised here, and actually this program can crash. Oh wait, no, it can't, because 0 is going to give you 0. It thinks it's something normal. Silly Python. So, yeah, it's not going to crash at all. We did a really good job, right? All right, so now we want to get a little bit more specific. So I'm going to catch a value error. So I'm only going to handle this one type of exception, because that is, so it still works. All right, A, something happened. But now we know that it's because I did something silly. And now I can break the program because, this keyboard interrupt that's actually an exception. When you hit Control C, it's gonna break you out of the program, but because we were catching that exception, it just kept going.
And then you'd be really.
Watch.
It'd be awesome. Yeah.
Wait, what?
I'm quoting the girls over there, so.
What are you?
Uh-oh. So something happened. Oh, wow. How did that happen? Oh, I know how that happened. What am I missing here? So I caught the keyboard interrupt, right?
Oh, yeah.
Yeah, I didn't go to the top of the loop. So what happened is it tried to execute this, but num2 hadn't been defined. So we're going to kick me back up to the top of the loop here. Yeah. Yes, it is a clean program. Anyway, so does everyone kind of get the idea with exceptions now? I don't have to go anymore. All right.
In these except up there, there's always comma E.
Yeah.
What does this E do?
So when you get an exception, when an exception is raised, it's actually an object, or there's an object that's associated with it. And in a lot of cases, you really you don't have to be concerned about it, but sometimes you want some additional information. So like, these are not very interesting exceptions, but some exceptions might have, some additional diagnostic information. So if you were, say, logging the run of your program and you wanted to diagnose any exceptions that were, you caught, like say you got a generic exception or you got something that was kind of odd you weren't expecting, you could print out additional information. And so E is the name of that object. So I can do this, all right? Well, this is because all right, if you give it a parameter like that, it's going to put that message into the exception. So now I can retrieve it when the exception is raised. So like, if I'm raising the exception, I can provide additional information. So that's the message that I put into the exception when I raised it. Does that make sense?
Well, how is that different? So is it basically the same thing as saying print, don't give me an even number?
Yeah, so, this is a really toy example, all right? So this is just going to print out whatever message that I passed in. So when I say this and point to my screen, I really meant this and highlighted this, okay? So this line is just going to print out this message that I passed in when I raised the exception, okay? Because what I'm actually doing is I'm creating a value error object that has this message associated with it. And that's what gets passed up this exception chain. And until I finally handle it here, and E holds the reference to that value error object.
So E is an actual value error object.
Yeah, so if I do something like this, and I print out the type, you see that? It's pretty neat. But did that answer your question? Okay. Could it be anything? So like, let's think of something like this. Like a list?
No.
I meant in your accept value error dash.
Oh. any name?
Yeah.
I've always used E, that's kind of the convention, but I think it'd be fine doing that. Like, E is the convention that I use, but you know, some people don't like that. They're like, well, we should name it something a little bit better, but honestly, why bother? Okay, are we good with exceptions? Did that answer your question? Any other questions on exceptions?
Is there like a built-in amount of errors that have like value errors, or can you make up your own?
Can you make up your own exceptions? Yeah, you can do that. You can say, all right, but, and, I think this is going to work. It's been a while since I've defined my own exceptions. We'll see. So, and again, you know, I can handle it. So if you ever work on big systems, a lot of times they'll have their own exception hierarchies that define all sorts of exceptions for the specific application you're working on. Python's exception or built-in exceptions are pretty rich. So there we go.
Did you have to inherit from exception?
I don't think you do. It's convention. It's like I could probably do this, I think. Oh wait. The only difference, or the only problem is that now, see, I expect my exception to have a message attribute, and I don't have anything on this, so I have to do this. Or something similar, right? I have to define message on this. And I think this will work. Hey. Oh, actually it does guard against it. So yes, you do have to inherit from exception. It's one of the few things that Python seems to guard against. So, I guess that answered your question. We good? All right. So we're getting kind of late. The only other topics that we have are the simulations and kind of the distributions, and that's about it. So, are there any questions on Monte Carlo methods? We've kind of done those to death, right? Real quick, someone humor me, what is a Monte Carlo method? I guess not.
The user design something for trials to like predict an outcome.
Right. So, what's that?
Gets data about something based on sampling it.
Yeah, it computes some value or solution to a problem using a random process and repeated trials. So, what's that?
Is it almost brute force?
No, it's not what we call brute force. No. I mean, it's like we computed pi by throwing a dart at a chalkboard or something like that, right? And it landed in a square, and we used some sort of analysis to figure out what pi was based on that, you know, throwing a dart at a board, you know, 1,000,000 times, right? So, I mean, that's what a Monte Carlo method is. Anything that uses random stuff to compute a value, or random simulation. All right, where'd my chalk go? Okay. And we saw a couple of Monte Carlo methods, like when I showed the solutions for problems 3 and 4 on the quiz. I used a random number generator in order to figure out the probabilities of like not rolling a 6 and all that stuff. And I used also the Monte Carlo method to show me that I was wrong on my initial answer for rolling exactly 1 6. So, Yeah. So is everyone comfortable with coefficient of variation? Because I did that first initially. Confidence intervals and levels. Does anyone have any questions on that?
What is
What
it?
is a confidence interval and a confidence level? Okay. So let's say I do a political poll. Let's say I do a political poll and I sample 1,000 people in a population, and I say 46% of them will vote for candidate X. My margin of error is plus or minus 4. And my confidence is 95. What this is saying is that if I conduct this poll, the same poll with, sampling 1,000 random people at a time over like 100 trials, so I do 100 polls, what I'm saying is that 95 out of 100 of those times, my level of support for candidate X will be between 42 and 50, right? Basically what you need to know for confidence levels and intervals. The other thing that you need to know for confidence levels and intervals is that if you have a normal distribution, with a standard deviation sigma, then one standard deviation from the mean is going to have, is it 66 or 67? Is it 68? I wrote it down, 68. Thank you. And then 2 standard deviations is going to be 95. And then 3 standard deviations is going to be what, 97? I think? Or is it 99.7? 99.7. So, but you need to just know that for normal distributions. That's all. So like, if this is 1 standard deviation, it's saying that 68 of the sample points are going to be within 1 standard deviation of this mean. And then if you have 2 sigma, then that means 95 are going to be within 2 sigma of the mean. And then if you have 3 sigma, then 99.7 are going to be within 3 standard deviations of the mean. So I think that's all you really need to know for the confidence intervals and levels, and also for normal distributions. Okay. So we're actually kind of at the end of the review session. So, does anyone have any questions that I haven't answered? No? All right, I'm done.